We are going to perform a reaction time calculation. Our example tells us if a dollar bill is 6.14 inches or 15.60 centimeters long, what would my reaction time need to be in order for me to be able to catch a dollar bill dropped by another person without, of course, moving my hand? We are told to assume that wind resistance is negligible. When we're told to assume wind resistance is negligible, that means that if an object is moving at or near the surface of the earth, it is accelerating at g, or the acceleration due to gravity, which is 9.8 meters per second downward. Okay, so here is what the problem would look like in the real world. Here's my hand. Here's the dollar bill which I am trying to catch. And we're going to give me the longest possible time to catch the dollar bill. So I'm going to place my fingers at the very bottom of the dollar bill. And then a person is going to drop the dollar bill, and the dollar bill will then fall, accelerating due to gravity. And I'll give myself the entire length of the dollar bill to catch the dollar bill. So let's look at a point at the top of the dollar bill and talk about how far that dollar bill has to fall before I catch it. So we're going to say that the initial position of the top of the dollar bill is right here. The dollar bill will then fall. The final position of the top of the dollar bill is right here. So final position right here. Thus, this is the displacement of the dollar bill, which is just the length of the dollar bill. Thus, the displacement of the dollar bill is 15.60 centimeters, or if I convert that to meters, all I have to do is take my decimal point and move it to the left 2 places. So my displacement, or the displacement of the dollar bill, is then 0.1560 meters. Quite often it is convenient to establish the positive position not to be upward, as you will see quite often, but to be downward. And this is one of those cases. I want to say that the positive direction is downward. And the reason that I've decided that is because the dollar bill is moving downward. Quite often it is convenient to say that the positive direction is whatever direction the object is moving. Because the positive direction is downward in this case, because we've established, or because we've decided the positive direction is downward, because the dollar falls downward in the positive direction, the displacement of the dollar is positive. If we look back at the problem instructions, we're told to assume that wind resistance is negligible. Thus, the acceleration of the dollar is the acceleration due to gravity, which is 9.8 meters per second downward. We've already decided that downward would be the positive direction, and so that means that the acceleration of the dollar bill is positive 9.8 meters per second. The only other thing that I can think of that we know is the initial velocity of the dollar bill right before it was dropped, and that is 0 meters per second. If you think about it, the instant the person dropped that dollar bill, it was at rest. So we know the initial velocity of the dollar bill to be 0 meters per second. So here's what we know. We know the displacement of the dollar bill is positive 0.1560 meters. It's positive because it falls down, and we say down is the positive direction. Acceleration is positive 9.8 meters per second. Again, it's positive because we've decided that downward is the positive direction. The last thing we know is the initial velocity of the dollar bill is 0 meters per second. Now we have to decide what it is that we're looking for. And if we go back up to the problem statement, it asks us to find reaction time. The thing we're looking for is time. So our goal is time. We want to figure out what t is equal to, time. So we know displacement, we know acceleration, we know initial velocity, we want time. So over here in the purple box we have some formulas for accelerated motion. And we need to decide which of these 6 formulas we will use to work this problem. Now here's what I do. I try to find a formula that has only those things I know, so only displacement, acceleration, initial velocity, and that thing I'm looking for, so t. So we've got to look through these 6 formulas and figure out which one has only displacement, acceleration, initial velocity, and time. And if we look around, that would be equation number 5. Equation number 5, which says delta x, or displacement, equals initial velocity times time plus 1/2 times acceleration times time squared. So we'll use this formula to try to solve for time. So here is our formula. Delta x equals initial velocity times time plus 1/2 times acceleration times time squared. Because I'm a physics teacher, before I start plugging values in for the variables, I like to go ahead and figure out if there's anything that might cancel out. In other words, are there any terms here? So here's a term, here's a term, here's a term. Are there any terms here that would be equal to 0 and just go away? So if we look at the stuff that we have, here's delta x is 0.1560 meters. That term, not going to go away. We have acceleration, 9.8 meters per second. If we plug it into this term, I don't think that'll make this term go away. Initial velocity is 0 meters per second. If we plug 0 in for initial velocity here and multiply it by t, 0 times anything is 0. So this middle term, initial velocity times time, goes away. So what we have left after this middle term goes away is displacement equals, again, v initial times time goes away because v initial is 0. So displacement equals 1/2 times acceleration times time squared. Now, before I start plugging in values for the variables, I will solve for whichever variable it is that we are looking for. And in this case, we're looking for time. So we're going to go ahead and solve for time. Okay, to solve for time, we will first multiply both sides of our equation by the inverse of 1/2, which is just 2. So on the left-hand side, we're left with 2 times delta x equals, and if we multiply the right-hand side by 2, we have 2 times 1/2, which is just 1, times acceleration times time squared. Again, our goal is to get t by itself, so at this point we can divide both sides by acceleration. So on the left-hand side we have 2 times delta x, or 2 times displacement, divided by a. Again, we're dividing both sides by a to get t by itself, equals, if we divide the right-hand side by acceleration, we just have t squared left. We're almost there. T is almost by itself. To get t alone, we need to take the square root of both sides of the equal sign. So square root of everything on the left-hand side that up just a little bit. So square root of everything on the left-hand side of the equal sign. So square root of 2 times delta x over acceleration equals, and if we take the square root of the right-hand side, we just have t. Now it's at this point that I feel compelled to tell you, as a former math teacher, that anytime you take the even root of both sides of an equation, you technically need to put a plus and minus, so plus and minus, on one side of the equation. The reason that we don't really have to do that in this case is because the thing we're solving for, time, can never be negative. So we are just left with the positive square root. We don't have to put that plus or minus in front of it because time can never be negative. Okay, so it's at this point that I've solved for time that I can just go ahead and start plugging in the values that I know for delta x and acceleration. So let me get this scooted down a little bit. So delta x we know is positive 0.1560 meters. So square root of 2 times delta x. And again, delta x we know is just positive 0.1560 meters. Acceleration we know is just positive 9.8 meters per second per second. All of this still equal to t. Now all I have to do is plug this stuff into my calculator. So I have 2 times 0.1560 equals, divided by 9.8 equals, and then I have to take the square root of the whole thing, and I have 0.178 when rounded to 3 decimal places. So 0.178, let's double check it, yes, and the unit for time is the second. So in order for me to be able to catch a dollar bill when dropped by another person without moving my hand, my reaction time would have to be 0.178 seconds.